Okay, next section, 3.3, we're going to be looking at optimization problems. We're going to be applying everything that we've learned from 3.2, 3.1 in order to figure out the best value that we can come up with. Now, the best value could sometimes be the highest or sometimes it'll be the lowest. And we will have to try to understand everything that we have learned and apply it to different situations. What we're going to be doing is we're going to be going over the examples from the textbook while we discuss what's happening in them and try to figure out what we need to do. So we're going to start with example 1 on page 141. A farmer has 800 meters of fencing and wishes to enclose a rectangular field. One side of the field is against a country road that's already fenced. Now the farmer will need to enclose the other 3 sides. The farmer wants to enclose the maximum possible area to use all of the fencing. How does the farmer determine the dimensions to achieve this goal? In a lot of these questions, you have to do what you're comfortable with. For me, I would always encourage a diagram, a visual to help you understand what's happening will be beneficial, especially as the questions become more complex. So we know that there's a road here. There's already a fence here. We want to build a fence here, here, here. We know the shape has to be a rectangle, and we have 800 meters of fencing to use. Because this side already exists, there's going to be 3 sides that need to be built. Because it's a rectangle, we know this and X and Y, whatever, we're just labeling it like this for now. In order to find the maximum area, we want to optimize the area, which means we need an equation for area. We've already done optimization in the previous section when we found out what is the local, or what are the extreme values, the max and min values within an interval. This will be the same thing. There's going to be an interval because you only have 800 meters of fencing available. You cannot find what the maximum area would be. If the question gives you an answer that the maximum area is going to be achieved when you have 900 meters of fencing, that won't work because 800 is our max. So what do we start with? We're going to start by making an equation. The area, we'll say with respect to x. So x will be the measurement. Normally, it's supposed to be x times y, length times width, or length times width, but we need to replace the y. Well, I know that 1, 2, 3, these 3 sides have to add up to 800, so I know the equation would be 800 has to be 2 x's plus a y. So isolate for y, take 2x over, 800 minus 2x will be equal to y. So I adjust my equation, x times 800 minus 2x. This is now my area equation with respect to the width. Next part now, we have our equation, we need to optimize. Your process for optimization is exactly that we finished doing in 3.2. Find the derivative, set it equal to 0, and with the x, solve for x. Once you have the x values, you're going to compare it to the extreme values and see which one gives you the highest y value, the highest area. So let's do that here. In order to make this simpler, I'm going to expand this, 800x minus 2x squared. The derivative will be 800 minus 4x. I'm going to set the derivative equal to 0. 800 minus 4x, and I'll get the x value is going to be 200. So x equals 200 is 1 point here. Now if x is 200, we can determine what the y value will be, but we're going to do that later. The first thing we need to do is figure out what are extremes. What's the smallest value that x can be? Well, x can be 0. Technically greater than 0, but x can be 0. It can be 0.1. And what's the largest value that x can be? So it has to be greater than 0. Actually, let's do that here. What we know is that x has to be greater than 0, and x has to be less than, you can say 800, because if x is 0, then the other side would be all 800 meters are being used up. Has to be less than 800. So in order to figure out our values, we're going to check a at 0, a at 200, and A at 800 in our area equation. So if x is 0, it would be 0 multiplied by something, so the area would be 0. If the area is 200, so if we do 200, so 800 minus 400 would be 400. 400 multiplied by 200 would be 80,000, right? Yeah, would be 80,000. And then the area at 800, again, 800, sorry, it wouldn't be less than 800 because there's two sides to this. It would be less than 400. So 800 minus the 400 times 2 would be another 800, so 0 multiplied by anything, that'll give me 0. So you can see here that the maximum area is achieved here. So the dimensions that would create the largest would be 200 by something. And we still need to figure out what y is. So y is equal to 800 minus 2 times 200, so that's 400. 200 by 400 would give us the maximum area. Okay, let's take a look at, I'm going to get ready for the second example. Okay, example 2. A piece of sheet metal, 60 centimeters by 30 centimeters, is to be used to cut or is to make a rectangular box with an open top. Determine the dimensions that will give the box with the largest volume, and then we're given a diagram. So there's a piece of metal, we'll draw it here this time, which is 60 by 30. We're going to cut squares that are equivalent on all four sides, meaning this and this and this and this and this and this. All 8 of these sides are going to be the exact same. They're going to be the exact same measurements. And once we cut that out, this part here will disappear. And once you fold these up, if you fold all of this up, you're going to create that box. I'm going to draw these back in so that we can make sure we understand what we're doing here. Now, what the question is asking for is to determine the dimensions that will give the largest volume. So what do we need? We need an equation for volume. And then we can use, after we have the equation for volume, we can determine, once we have the equation for volume, we can determine what the optimized value would be. So the volume is length times width times height. Now in this case, your length will be here, your width will be here, because once the box is made, this part is gone, right? This little bit has been cut off from each part. So this is the length, this is the width, and this part here would be the height. Now, we know that this whole thing is 60, and this whole thing is 30. So what we would do is say the part that's been cut off, we can label that as x. So for my length, it was 60, then I cut off an x here, and I cut off an x here. So that would be 60 minus 2x. That's the length. For the width, same idea on the other side. This whole thing is 30. We cut off an x here, and we cut off an x here. So that would be 30 minus 2x again. And finally, the height we know is here. That's h. That's the part that's getting cut off. So there would be, sorry, not h, it's x. So we have our equation. 60 minus 2x times 30 minus 2x multiplied by x. And therefore, we have the volume with respect to x is 60 minus 2x times 30 minus 2x multiplied by x. And we can start our process. Once again, find the derivative, set it equal to 0, solve for x, compare it to the the extreme values. Let's understand what those extreme values would be. So now we know x has to be greater than 0 because the smallest you can cut is nothing. And what does it have to be less than? Well, if we go based on this part, if it's 60, we can only cut half. So it has to be less than 30. But for this part, which is 30 centimeters as it is, What can we cut from 30? We can't cut more than 15. Because if we cut more than 15, those two are not equal anymore. We can cut 15 from each side, which means x has to be less than 15. So we have our domain, or our restrictions for the x values, has to be between 0 and 15. Let's go through and solve this. First step, find the derivative. Actually, first step, I'm going to, let's just find the, let's simplify it a little bit and let's find the derivative. So what you can do is you can expand everything and put it into a polynomial function. So 60 times 30 will be 1800. 60 times 2 is 120, and 2 times 30 is 60. So negative 120 minus 60 is negative, what am I saying? Negative 180 minus 60 would be negative 240x. Okay, I'm confusing this. Let's do this again. 60 times 2 is 120, minus another 60 is negative 180x. Negative 2x times negative 2x is plus 4x squared. And all of this gets multiplied by x. So 1800x minus 180x squared plus 4x cubed. Now we're going to find the derivative. 1800 minus 360x plus 12x squared. Now we're going to set the derivative equal to 0 and find the factors. In order to find the factors, I'm just going to check if 12 can be factored out. I know 12 can be taken out of here. Can it be taken out of 1800? I'm going to cheat a little bit and say yes, it can. So I can factor out a 12. So this is going to be x squared minus 30x plus 150. Just to help me simplify this a bit. So once I factor out the 12, I have x squared minus 30x plus 150. Two numbers that multiply to be 150 but are negative 30. That's not going to happen because two numbers that multiply to be 150 would have to both be negative. And I can't find two negative numbers that are going to add up to be negative 30. So what we're going to have to use is a quadratic formula. So x is going to equal 30 plus or minus square root of 30 squared minus 4 times 1 times 150, all divided by 2a, and the a value here is 1. Let's cheat a little bit again and see the two values are going to be 23.7, or x is going to be 6.3. Those would be our two answers, 23.7 and 6.3. We know though that 23.7 cannot be used because it has to be less than 15. So we have x is equal to 6.3, and then we're going to check 0 and 15. So we're going to check the volume at 0. Volume at 0 would be 0. The volume at 15, if you put 15 into here, that would be 0. That would be 0. And the volume at 6.3 is going to give us 5,196 centimeters cubed. That is your largest volume. But again, that's not what the question is asking for. The question wants to know what dimensions will provide the largest volume. So the dimensions are going to be when x is 6.3. The height is 6.3. The width is going to be 30 minus 12.6, and the length would be 60 minus 12.6. If you go through with that, you will find that, where should I write this? What we're going to find is that the dimensions that will maximize the volume and create the volume of 5,196 are going to be 6.3 by, what do we got? 17.4 by 47.4. Again, don't overcomplicate things. There will be one part that's going to be difficult in this process. That's the first step. what is your equation going to be, and how do you simplify your equation? What equation do you make? How do you simplify it? Because a lot of times the equation that you make will have multiple variables in it, and you have to be able to create alternative equations, separate equations, that can help you replace the variables in your equation. Once you have your equation, find the derivative, set it equal to 0, solve for x, and check each x value to see which one would give you the highest or the lowest value, depending on what the question is asking for. Okay, thank you.